Extreme values of functions. Okay, so using the case 1, we're going to look at an example that goes with that. So we're going to find any max, min, or inflection points on the graph of f of x equals x cubed minus 5x squared plus 3x plus 6. So this is just like a normal like curve. So essentially the first thing, we're just going to follow the steps that you have in your notes. So step 1 is to find the y prime and y double prime. So the first derivative would be 3x squared minus 10x plus 3. And then second derivative would be 6x minus 10. So it's not necessarily that it has to be done in this order, but this stuff just allows you, it like just sets you up for the rest of your problem. So then the next step is we're going to find all critical points of y for all x for which the first derivative is equal to 0. So we are going to take our first derivative equation and set it equal to 0 to solve it. So I'll have 3x squared minus 10x plus 3 equals 0. And then essentially I would see if I can factor this. And so negative 9 and negative 1 would work. So I would have 3x squared minus 9x minus x plus 3 equals 0. And then factor by grouping. Take out a 3x. I'm left with x minus 3. I'm going to need to take out a negative 1 for it to match. So then that's x minus 3. So I have 3x minus 1 and x minus 3 equals 0.
Where'd you get the 3x squared minus 10x?
That was the first derivative.
Oh, okay.
I'm just taking the first derivative and setting it equal to 0 here in that step. This is going to find our critical points for us. And not necessarily that you're going to have, like, to the fullest extent of this, but this kind of question where it's asking you to find all of these different things could very well be a short answer type question on the exam. So that's why I spend like more time with it, because it's just a lot of information, but stuff that you need to make sure that you know how to do, because you may not use it directly, but you may indirectly need the information from it to find other things that you're looking for. So if we set each piece equal to 0, I would get that x is equal to 1/3 or x is equal to 3. So these are my critical points. So then step 3 says, let C be a number for which y prime is equal to 0. Check the sign of y double prime at C. So essentially we're going to see if the value, when I plug in these numbers, if it's equal to 0, greater than 0, or less than 0. So the first derivative evaluated at 1/3 is equal to 0, because that means that that's a critical point. So ordinarily I wouldn't necessarily write this, but just for reference here for y. So then we want to evaluate the second derivative at 1/3 to see what's happening. So that's why we went ahead and found the second derivative in step 1, just so that we already have it. We're not like, I used to like bounce back and forth, but it's like I'd rather just have both derivatives there. It's just easier for me to find. So we plug that in. We have 6 times 1/3 minus 10. So 6 and 1/3, that just becomes 2 minus 10, so that's -8. So that means that f double prime of 1/3 is less than 0. And if it's less than 0, that means that it's a max. And specifically, we would say it's a max at 1/3 and then f of 1/3. And so to find that, I would take and plug in 1/3 to my original equation. To find what that y value is, where the max is actually occurring. Because the first and second derivatives are helping us find critical points and then where I have a min and max. But the min and max are actually occurring in the original function. So we're going to plug in 1/3 to this to find what it is. And so f of 1/3 would be, go back and find where the original equation is so I can't keep scrolling back and forth. So 1/3 cubed minus 5 times 1/3 squared plus 3 times 1/3 plus 6. So that is, honestly, for time, I'm just going to plug it into the calculator. I don't feel like doing that right now. Now, my calculator gave it to me as a decimal, but I turned it into a fraction. Just since my x is a fraction, I'm going to leave it that way. And it would be 175 over 27. So then this point here would be technically 1/3 and 175 over 27. Which as a decimal would be like 6.48 approximately. But we're not really doing anything with this otherwise. We would be able to take and graph our function with the information that we're finding ultimately. So that's 1/3. We also need to check at 3. So f prime of 3 was equal to 0. So because that's the case, now I need to check the second derivative at 3. And so that would be 6 times 3 minus 10. God, I keep trying to put parentheses on things that don't need parentheses. So 18 minus 10, so that would be a positive 8. So that means that the second derivative evaluated at 3 is greater than 0, which means that I have a min at 3 and f of 3. And then we would find f of 3 the same way. Just plug it in. So f of 3 is equal to 3 cubed minus 5 times 3 squared plus 3 times 3 plus 6. So we've got, what is that, 27 minus 45 plus 9 plus 6. -3, I think. So then that means that our min is at 3, -3, if we actually want to find the point. So in our case, both our second derivatives, when evaluated at these 2 points, were either greater than 0 or less than 0. That's the scenario that we hope for, because if it's equal to 0, then there's a whole lot more work to do, which we'll see in our, I think we'll see in our other example. But step 4 is unnecessary for this problem. Now, ordinarily, I wouldn't write this either, but I'm just going to write unnecessary for this problem because we didn't have that situation. That's only if the first derivative evaluated at the value is 0, meaning it was a critical point. And then when we plugged it into the second derivative, it was also equal to 0. And then we have to look at the sign of y prime as x goes through that point. So as x goes from smaller to larger, what happens to our y value? And then that'll help us to see what we need to see with that. So then our step 5 says find all x values where y prime is equal to 0, y double prime is equal to 0. These are possible points of inflection. If c is an x and the sign of y double prime changes from positive to negative or negative to positive as x increases through that point, then the x coordinate is a point of inflection. If the sign does not change, it is not a point of inflection. So we're taking the second derivative and setting it equal to 0. So that would be 6x minus 10 equals 0. So that would mean x is equal to 10 over 6, or 5/3. So obviously this is bigger than 1, less than 2. So I'm going to look at what happens as x goes from 0 to 2. Because I'm looking for points as x goes from smaller to bigger. Is it changing from positive to negative? It's kind of like if you remember doing those sign charts last year briefly in pre-cal. It's kind of like that, but I'm not actually doing the sign chart. I'm just seeing what happens as I go through this point. So if I plug in 0 to the, where is it? Second derivative, then I get negative 10. Let me mark that. 2. And then if I plug in 2, that would be 12 minus 10, so that would be a positive 2. And so that goes from negative to positive. So because it changes from negative to positive, let me see this, as x increases through 5/3. So there is a point of inflection at 5/3 and f of 5/3. And so if I plugged in 5/3 for into f, I'm not going to do it for the sake of time, but that would end up giving us 5/3 and 47 over 27 for that point. So with all of that information now, I could sketch a graph of this roughly with the information that I have. I know that I have a max, where is it? At 1/3 and 175 over 27, which I think we said was like 6 point something. So I could say, okay, well, I have a max somewhere up here, and I'm just doing a very rough sketch. I know that I have a min at 3, -3, and a point of inflection at 5/3 and 47 over 27, so that's about a little less than 2 on both of those. So somewhere in here would be my point of inflection. So if I know that was a max, we're coming down through. Obviously, I don't know what else is happening to my graph. It's a cubic function, so it most likely is turning around one more time somewhere. Not necessarily true, but because we can have double zeros. But anyways, so roughly this is what my sketch would look like with the information that I'm given. It often isn't asking you to actually sketch it. It's usually just asking you to find the information that we found. But like you can see, that was just one problem. So it makes for a long, like, set of problems. And there are other things that we'll be doing with these as well, between this section and coming section. So a lot of times what I do on like a quiz and a test is I'll just have you do one problem where you're finding everything, because the problem is if you're not careful, what ends up happening is it'll take you 3 days to take a test, because you're going to find all this information about this problem. Well, what's to come still is things that you need all of this information to continue doing. So that means you'd have to find all this information for another problem to go one more step farther with it to get your next thing. So I usually, instead of doing it like a normal quiz where it's like, okay, here's all 5.1, here's all 5.2, whatever, it's just like all smushed together into one problem. So you have one long problem for this. And there's other small things mixed in too, but only one where you're finding absolutely everything essentially. But obviously we're going to do a lot more examples before we get to that point. So so you said you do not have anything written down for case 2 note-wise. Okay. So that was your case 1. Your case 2 are functions whose derivatives may not exist everywhere. And where we skipped step 4 because we said it was unnecessary, it's very rare that a problem needs a step 4. I think we may do one example of that, but I actually realized the next example that we're doing is something totally different. But this step is super rare. We might look at one problem that has it, because it's very hard that you have something that makes your first derivative 0 and your second derivative 0. So anyways. All right, so if there are values of x of which a first or second derivative does not exist, so D and E, I think we've talked about it before, but that does not exist, consider those values separately. And recall a local max or min is one of transition between intervals of rise and fall, and an inflection point is one of transition between intervals of upward and downward concavity. So that's why in this previous problem, where this was a max here and then a min, our inflection points between that, because that's where it's changing from a downward concavity to an upward concavity. Or obviously depending on the situation. All right, so a short example, then one that we'll actually kind of work through a little bit more. Y equals x to the 2/3. Well, the first derivative would be 2/3 x to the negative 1/3. Or we could write it as 2/3 x to the 1/3. And then y double prime, I'm just going to write it over here, is going to be negative 2/3 x to the negative 4/3. Or we can write it as negative 2 over, oh wait, this was supposed to be a 9. Wait, 3 in front, no, wait. This is why I have to do it this way. 2 over 9, yeah, there we go. Negative 2 over 9x to that. So negative 2 over 9x to the 4/3. So with that information, what would happen if x was equal to 0?
Whole thing would just be 0.
Well, what happens if I have a 0 on the bottom?
It's undefined.
Yeah, it's undefined. So that means that neither derivative is 0. Because both of those situations would cause a problem. So both derivatives fail to exist when x equals 0. So as x increases through 0, y prime changes from negative to positive, and that's because if I plugged in, say, negative 1, then this is going to be negative my y prime. If I plugged in positive 1, it's going to be a positive number. So negative to positive. So 0, 0 is a min. And then we can also say that y double prime is negative everywhere except 0. Because no matter what I plug in, it's being raised to the 4th power. That's going to become positive, and my number on top is negative. So it's going to be negative everywhere. So the curve is concave down because it's negative. So essentially, I have what this function would look like. We did this back a little bit when we were talking about like the cusps and corners and all of that. But essentially, it's one of those graphs that kind of looks like a bird. All right, so our last example, kind of using all of this stuff combined now. F of x equals x to the 4th minus 4x cubed. So the big thing is going to be remembering when I find a value, which function is it getting plugged into? Is it getting plugged into my original, to my first derivative, or to my second derivative? Because that's typically where people go wrong. So we'll try to really emphasize like, okay, this is getting plugged in here for this situation and stuff. So what would my first derivative of this be?
4x cubed minus 12x squared.
Yep. Fortunately, with these derivatives, they typically try to be nice to you, and it's not like a bunch of chain rules and all that stuff like we've been having. So kind of back to easy derivatives for a little bit. Everything else gets harder. And what would second derivative be?
12x squared minus 24x.
Yep. All right, so then I'm going to set my first derivative equal to 0 and solve. So we've got 4x cubed minus 12x squared equals 0. I would take out a 4x squared. That would leave me with x minus 3 equals 0. So that tells me that x equals 0 or x equals 3. So these are my critical points. And then I'm going to check each one. And just because of the nature of I know what's going to happen, I'm going to check 3 first. But ordinarily, I would just check them in order. So f double prime of 3. To check for a min or a max, I'm evaluating at these critical points. We have 12 times 3 squared minus 24 times 3. So we've got, let's see, 9, 12 is 108, minus 72, 36. So that means that that's a positive number. F double prime of 3 is greater than 0. And a lot of times, rather than writing it this way, let me write what I normally would do. I'll just come over here at the 36 and write greater than 0. And so then I'll say min at 3 and then plug in 3 to the original. So that would be 3 to the 4th minus 4 times 3 cubed, 81 minus 27 and 4. Why am I struggling with that? Is that 108? Negative 27? Does that sound right? I think that's right. Struggling with basic maths today, apparently. All right, so there's that one. So now I'm going to check at 0. So f double prime of 0 is 12 times 0 squared minus 24 times 0. Well, in this case, everything's going to be 0. So this means that the second derivative test fails. So that means that I'm going to have to do step 4 on this problem. So this one did end up needing it. All right, so step 4 said if the first derivative is equal to 0 and the second derivative is equal to 0, evaluated at the critical points, then check the signs of y prime as x increases through c. So I'm looking at what happens to the first derivative as we go through that critical point value. So f prime of x as we go through 0, so my first derivative, if I say negative 1, then I've got that's negative and that's negative, so that's going to be negative. So negative at negative 1. And then if I do positive 1, I would have 4 and then minus 12, so that's still negative at positive 1. So the sign doesn't change. So that means that it's neither a max or a min. So we can have critical points that aren't maxes or mins as well.
Why did you use negative 1?
Because we're going through the critical point, and the critical point that I was using was 0.
I still don't get it.
So we checked each of the critical points that we got here into the second derivative for the second derivative test. If it's greater than 0, it's a min. If it's less than 0, it's a max. If it's equal to 0, we have a problem, and it fails the second derivative test. So that's what happened with this point at 0. So step 4, see if I can put it up here, from your original stuff, the original notes you had, says that if the first derivative evaluated at the points equal to 0 and the second derivative evaluated at that point, these are the critical points, that's why it's C, are equal to 0, then we check the signs of the first derivative as x increases through C. So since my critical point was 0, I just chose to use -1 and +1. I could have used -5 and +100 if I wanted to. I'm just looking at, now, you have to be a little bit careful. I would choose a number less than this when you're doing it because you could potentially end up with a problem if you use a number that's too extreme. So, I mean, I wouldn't go crazy with it. That's why I try to stick around, like, basically ±1 of whatever that critical point is if I can. And so then, if the first derivative is greater than 0 for x less than C, this is the part where it gets a little bit confusing. But it has to change signs. Ours did not change sign. So if the first derivative is greater than 0, but for x less than C, so that means -1. That was our -1 in this case. So -1 was less than 0. So if the first derivative is greater than 0 for this, but the second derivative, the first derivative is less than 0 for 1, because that's greater than 0, then where there is a tangent line as x increases through C, there's a local max. If the situation is reversed so that it changes from negative to positive as x increases through C, it's a local min. So our situation was that the sign did not change. So essentially, if the sign changes from, let me make sure I say this right, from positive to negative, then it is a max, local max. If it changes from negative to positive, then it's a min. Our situation was, it was negative the whole time, though. At -1, when I plug in -1 to the first derivative, it's negative. When I plug in +1, it's also negative, so it does not change sign. So essentially, what that's telling me is it's not a max or a min.
Okay.
This situation is so rare, I wouldn't even stress over it. Like, I've only seen a handful of problems ever that this happens that they're going to give you at this point. I'm not going to say, like, you never would if you have to take more math, but pretty much they're going to give you the original scenario we had with this previous problem up here, where both of them end up working, so we didn't even need to do step 4. I think there might be one problem in the book that I've seen that needs a step 4 out of who knows how many problems are in this section. So f prime of x does not change sign. As x increases through 0. And I could write it out with, like, you know, all the fancy, you know, x is less than C and whatever values if I wanted to, but I just think it gets excessive, and so we don't really need to worry about that. So 0, 0, because if I plug in 0 to the original, it's just equal to 0, is neither a max or a min. Now, eventually we'll have something where if that happens, like, what is that 0 value? But, again, not something to worry about right now. So then our step 5, find all x values where the second derivative is equal to 0, because these are possible points of inflection. So y double prime is equal to 12x squared minus 24x. So we set that equal to 0. I can take out a 12x. That's left with x minus 2. So x is equal to 0 or x equals 2. So I'm looking at what happens very similarly to what I did here as x goes from, or as we go through these values. So as I go from negative to positive, what's happening on here? So for the sign of the second derivative, if I look at this, so I'm just looking at this equation here. If I do -1, this is positive, so that's positive. So let me do this. So 0 is +2, or like going to. If I try +1, well, this is positive, but this is negative, so my answer is going to end up being negative. So as we go through 0, I go from positive to negative for the sign. So f double prime changes sign as x increases through 0 from positive to negative. And we're going to see what happens. X does what through 2. So I'm going to fill in either increases or decreases essentially. So as we go through 2, increases, oh, okay, I don't know. Or wait. Oh, as x increases through, I don't know why, but I didn't need to write a blank there then. That's always increases. As x increases through 2, the stuff that goes in the parentheses is what could change. So if I looked at, say, +1, which I technically already used, so like over here. So +1, we get a positive, we get a negative, it's going to be negative. 2, if I choose 3, since it's on the other side of 2, that's going to be, let's see, 9 and 12 is 108, and then minus 72, so that's going to be positive. So this one goes from negative to positive. So as x increases, let me say as x increases through 2, we go from negative to positive. So that means that the points 0, 0, and 2, I haven't found this one yet, so 2 into the original would be 2 to the 4th minus 4 times 2 cubed, 16 minus 8 and 4 is 32, so that's -16. So 2 -16 are points of inflection. So in this case, both of them were points of inflection. In the last one, I don't remember what happened. We ended up having 1 point of inflection in the last one. So I know it's a lot, and you're probably like, what am I getting myself into with this section? Because it is, but we're going to spend a lot of time with it. This very well could be our last section before Christmas, just because of the amount of time it'll take us to like talk through it, make sure that we understand it. 5.2 usually is a little bit quicker, so we might be able to get through it as well. I think it's, if I remember correctly, it's like the mean value theorem, just pretty easy. So we'll probably try to get through those 2 sections and then have one more quiz. We'll definitely have a quiz. What it's on is a little bit TBD, but this is about as hard as it gets, and our book doesn't necessarily do everything to this level of doing it all in one problem, but this is an AP style question. Like, I pulled this from the AP book for a problem to do. So it's like would be what a free response question would look like. So
Yeah, I'm absolutely confused.
most people are for a couple of days, and then it starts to click a little bit. The beauty of the book, which is why I always go back and forth on which way I want to do it, is they do things step by step. But I think it's good when you've had the notes that go with this to see an example that matches your notes of like, okay, what am I ultimately working towards, even if you're thoroughly confused. And essentially what we'll probably do is when we go through the book and it does, like, the book's the first questions are just going to be, tell if there's a max or a min for this problem. Tell if there's a point of inflection or a critical point. Like, it's going to literally be, like, super step by step in the way that they break down the problems. We'll probably circle back to these and talk through them again, where you can, like, we can just sit and I can just scroll through and be like, all right, this is what we did with this problem, here's why, and then it'll start to make more sense combining everything together. And then we'll probably revisit this material after Christmas as well, because the rest of the chapter, like I said, kind of ties into it. But just enjoy break and don't stress about it. Don't think about calculus over break, and we'll pick it up next week.